Hello, my name is Luke Chamandy, and I'm going to talk to you today about the evolution of galactic magnetic fields. And this is based on the work that's listed here at the bottom. Now, our motivation for this study is that we want to model magnetic fields of star-forming galaxies to make statistical predictions for instruments like the SKA. Now, there could be several different approaches. One could extrapolate from observations of relatively nearby galaxies, which has been looked at in some works. But this is more of an empirical approach than a physical approach and neglects galaxy evolution to some extent. Another possible approach would be to use analytic dynamo theory, but then it's difficult to include the full diversity and evolution of galaxies. Another approach would be to use cosmological MHD simulations, and these have come a long way recently, but the resolution is still insufficient to capture the ISM turbulence and dynamo processes in the galactic disk. The method of our approach is that we first run a semi-analytic galaxy formation model known as GALFORM, which reads in a dark matter halo merger tree produced using output from a Millennium class N-body dark matter simulation. And then we obtain from this 45 snapshots of the global galaxy properties from z=6 to z=0. We then, using this output, we input this into our code magnetizer. So our code first updates the ISM and dynamo parameter values at every GALFORM snapshot. And then it computes an ISM model, which is 1D along radius and axisymmetric, assuming vertical hydrostatic equilibrium and including gravity from stars, dark matter, and gas. So once we have this ISM model, and this is all computed, it takes in these parameters from GALFORM and it adjusts the model at each step, at each time step that it runs into one of these GALFORM snapshots. And it evolves the large-scale magnetic field by running a mean field dynamo simulation for each galaxy. So each galaxy is on a different processor. So it's an embarrassingly parallel process, and each galaxy takes on average 10 seconds to compute. And these are fully nonlinear equations, so we do have a feedback from the magnetic field, which acts on the turbulence. So that theory is built into our model. Furthermore, when the galaxy undergoes a major merger, we reset the magnetic field. The assumption here is that the disk is basically affected or destroyed, I guess, and then the magnetic field resets to the seed value or floor value, which is based on some assumed average over the small scale component of the magnetic field. So the small scale component of the field, we have a simpler model to evolve that. We just make it some fixed fraction of the equipartition field, equipartition with turbulent kinetic energy. So rho v squared, that field. So small scale field, we evolve in that way. Large scale field, we actually run a more detailed simulation. So here's some results for the large scale field. These are just a few examples. We run over 1 million galaxies to get the statistics, but you can see that in what I'm showing here, the dark colors represent later times and the lighter colors represent earlier times. For example, the one in the bottom left, what you can see happening is that it first increases the field strength, and what I'm showing here is the toroidal component of the mean field. It increases exponentially from low values and from very low values, actually, some 10 to the minus 3, 10 to the minus 4, until it saturates. And once it saturates, there's a secular evolution where the field strength actually reduces. And you see at the late times, it's this dark curve. Another example, the one above, you see the difference being, it's similar, but the difference being that at one point during the simulation, the field got reset after a major merger and then the field again started to grow by the dynamo, but it happened to have the opposite sign. That's just random based on the random seed field. And then finally, another example in the top left is you see that the field can actually acquire a reversal along the radius. And in this case, it has 2 reversals along the radius. And these reversals happen relatively early on, and they get locked in even in the nonlinear, well, they get locked in the nonlinear stage of the dynamo. However, this is somewhat sensitive to the seed field chosen. So just to look at one interesting result, we can look at the statistics of the magnetic field strength as a function of time, redshift, and stellar mass. So B naught here is the volume average large scale field strength. And I'm showing the distribution at z equals 0 for Milky Way like galaxies. So the mass is in this bracket, in this range. And you can see that some of the the majority of the galaxies do contain a microgauss level magnetic field, although there are some that do not. And this is sort of where the seed field is. Okay, so we have a certain prescription you could read in the paper. And so for these galaxies, the dynamo never became active, most likely. And then you could also look at the maximum field strength, which will be a bit higher. And the seed, you can see more clearly where some galaxies just are left with the seed field and never actually grow their magnetic field substantially. And then you can look at this value relative to the equipartition strength. Equipartition is basically B equipartition squared is 4 pi rho v squared, where v is the turbulent velocity. And you can see that it's of order 1, and so these fields have actually saturated, and they've reached roughly the equipartition value. Then you could also look at dependence on stellar mass. So you see here, we've also plotted in dark blue the distribution for the smaller mass galaxies. And they're actually more like, so we see that the model predicts that the more massive galaxies are more likely to have large scale magnetic fields at z equals 0. This is still all for z equals 0. What do the observations say? Well, if we plotted here the number of the fraction of galaxies in a given mass bin that have an observed large scale field, and there's quite a bit of uncertainty, but the trend with our model, which is shown by the lines, the trends are similar. So you do expect a larger, or more commonly expect to get a large scale magnetic field in nearby galaxies if the galaxies are more massive. Now, one should be aware that these are small number statistics, and the data, interpreting the data is somewhat subjective because it's somewhat qualitative, the data. But in any case, this is the kind of thing that we want to compare our model to. And so we can explore also the magnetic field properties as a function of the redshift. And here I've shown the higher redshift, 2.5, compared to 0. At z equal 2.5, there are virtually no large scale fields present, except in a very small fraction of the low mass galaxies. And then as we go to z equal 1, where the star formation is quite high, star formation rate, we find that most of the high mass galaxies have large scale fields, and most of the low mass galaxies do not. And if you look at the full evolution, we see that the PDF of large scale fields, the field strength evolves more rapidly in the high mass galaxies. Now, there's no one reason for this. We looked at the various parameters and we tried to understand why the evolution is faster in the higher mass galaxies, and it's actually a combination of reasons. So there's no simple explanation for this. What is easier to understand, perhaps, is that if you look at the galaxies that actually have strong large-scale magnetic fields of order equipartition, which is given by this upper peak of the bimodal distribution, you see that that field actually increases with redshift or reduces with time. And then one could ask why. So that the reason is that if you look at this graph, now we're plotting the same thing, but it's Bmax over B equipartition. So relative to the equipartition field strength, you find that it's relatively flat. And so what this is telling us is that the strength relative to equipartition is roughly constant in time, which means that if the strength itself reduces with time, that means it's because the equipartition strength reduces with time. And so you're getting fields saturating at equipartition, but the equipartition is reducing with time. The reason the equipartition is reducing with time, it's basically rho v squared, and v in our model is just a constant. 10 kilometers per second is what we adopted. And so it's because the density, the gas density, is higher at higher redshift. And this is actually consistent with the result of Rodriguez et al. 2015, which is kind of the precursor to this paper, which adopted a 0D analytic steady state dynamo model. And so they assumed a steady state. They assumed that the field adjusted instantaneously to the changes in the galactic properties. We haven't assumed that in our work, but we find that the results are similar, which tells us that the large-scale magnetic field does adjust very rapidly to changes in the underlying galaxy properties. So what's next? The code has already been used to model FRB statistics. We are now working on modeling the radioluminosity function and actually predicting the radioluminosity function for both radio at a certain frequency, but also the polarized component of that. We want to, well, we have already modeled the turbulence parameters themselves, which are parameters in the dynamo model. So right now in this model I've described, we have VRMS equal 10 kilometers per second, tau, the correlation time of turbulence, also a constant. But now we know how, using analytic theory, how to model these in terms of observables, or in this case, parameters from Galform. So we can, if we better model these dynamo parameters, we can have a more sophisticated type of model. So that is a next step. We can also put in additional physics, i.e., like, for example, the tangling of large-scale magnetic field to produce more small-scale field, and other things as well. Explore the parameter space. There are only about 10 parameters. We want to explore the statistical relationships between our outputs, for example, the mean field strength and the pitch angle of the mean field, and then compare with observational data. We want to extend it ultimately to 2D axisymmetric, so include the vertical dimension and include the gaseous halos, which are known to contain fairly strong magnetic fields. So that's all, and please feel free to contact me if you're interested in using the coder if you have any questions. Thank you.